Okay, so here we go. So section 2.6 is a pretty quick one as far as our coverage of it. It's a long section. There's a lot of stuff in there, but it's all examples. It's like almost all of it is examples. So as I typically do, I'm going to do two of those examples. Before I get to the examples, there is one sort of barely new topic that I need to mention very quickly, and then we'll go on to those examples, and then we're going to move on from there. Okay, so I'm going to start off by reminding y'all of the vertical line test. So this is a geometric convenience, a way of thinking about a question, which is how to identify whether you're looking at the graph of a function or whether you're not looking at the graph of a function. So the vertical line test says if you're looking at a curve here. This goes back to single variable math. If you make vertical lines, is it the case that every vertical line hits the curve exactly once? In this case, yeah, right? So by the virtue of the fact that every vertical line hits this curve exactly once, this curve is the graph of a function. On the other hand, if we look at this curve, which I'm ominously highlighting in red, and you play the same game, well, some of these lines intersect the curve exactly once, right? And that's not good enough because there is at least one line, that being a nice example, that intersects this curve multiple times, right? So this is not the graph of a function. Functions are not allowed to look like this, right? Another way to say it. Okay, all right. So I just want to point out that there is this is a reminder. This is from single variable. Just want to point out there's a higher dimensional version of this. So here I'm going to, of course, all the only graphs we can draw pictures of in multivariable calculus are graphs of real valued functions on R2. So in other words, surfaces like this. And point out, same game applies if you want to know whether this surface here is that surface a graph. Well, you start looking at vertical lines. Whoops, I wanted to switch to the. Here's a vertical line that intersects exactly once, right? Likewise here, intersects exactly once. And appeal to your geometric intuition, interpret generously how I've drawn this, and the intended surface here, and I think you can persuade yourself that is indeed going to pass the vertical line test. On the other hand, this one doesn't. Right? So again, that surface, a vertical line is going to intersect there and there. Right, so this fails the vertical line test. So this surface is not a graph of a function. So it's morally identical to the single variable equivalent theorem. I just wanted to state it for the record here. Okay, that's all the new material in this section. Again, there are lots of examples. I encourage you to read all of these examples in this section, right? For it's a good example to work off of. I'm going to go through two of them. Well, kind of three of them. The first one being this one. And so let's talk about this question. How can we algebraically represent a certain line in R2? Now let me put that in context a little bit. We've talked about if you have a function, what are the different kinds of pictures that you can generate that represent that function? Well, you can make the graph of the function. You could make level sets of the function. You can draw the image of the function. These are all different pictures that we associate to one function. Here, we're kind of asking the question in the other direction. Here we say, well, we've got a picture. Is this the graph of some function? Might the same thing, the same line, might it also be a level set of course, a different function? The graph of this function, maybe it's the level set of this different function, and maybe it's the image of yet a third function, right? So that's what we're interested in. Now, this line is an easy line to draw. It passes through these two given points. So here it is. And the algebra of figuring out, what is the equation? Where is it? Yeah, here we go. The equation of this line, that's an Algebra 1 problem. I'll let you guys work out the details on that, like this 2x minus 1. Okay. That's not a function. Right, this is an equation. So we're going to look at this equation, and from that equation and manipulating it appropriately as necessary, or looking at the picture, working off of the picture as necessary. Can we find a function whose graph is the line? Can we find a function one of whose level sets is that same line? And then a third function whose image is that line. All right. So now, good news. Deciding if this is the graph of something is a pretty straightforward question. We're looking for a function f of x such that if you take the graph of it, if you set it equal to y, now keep in mind, right, this means graph. Setting the function equal to some other variable, and I'm choosing y. Is there a function whose graph has the same equation as that? So, well, it leaps off the page. What can you set equal to y to get 2x minus 1 equals y? Well, how about 2x minus 1? Right? No challenge there. And so that's the function. This is the function whose graph is that line. Is everybody happy with the argument there? Now let me show you where a lot of students go wrong on this, and it's a heartbreaking thing when I see this on the exam. Oh, it's makes me sad. Please don't make me sad. So lots of students will write instead of this. Lots of students will write y equals 2x minus 1. That's not a function. That's an equation, right? This is the equation of the graph of the function f that we're interested in, but this is not the function. Right? Does everybody see the problem? Now let's talk about how I would score this response on a midterm exam, where the question is, find the function whose graph is this line. The algebraic effort involved in getting to this equation is trivial, right? It's algebra 1, it's high school, maybe middle school level algebra. There's no challenge there. What would be the purpose of my asking a question like this on the midterm exam? The purpose of this question would be to test to what extent do you properly understand the meaning and use of the terminology. And that's what the student has not done, right? So this temptation to say, oh, but it's so close, right? And it's close in the trivial sense of, yeah, you did some algebra 1, right? But in the sense of, has a student demonstrating an understanding of what the graph construction is? Sadly, no. Right? So this is probably no credit. So please be careful with that. Now, for your convenience, questions of this sort has been on old midterms of mine on many past occasions. So you got lots of old examples to look at, and you'll see, how I wrote it. Sometimes I ask, find the formula for the function and indicate what the domain and target of that function are. Right? That kind of variations. But be very careful to realize that when you see a question like this, possibly on the midterm this semester, the point of the question, always try to understand the point of the question. Right? The point of this question is for you to demonstrate correct understanding of the terminology and to make correct use of that, appropriately in whatever the algebraic trivial challenge might happen to be. Okay, so next question. By the way, for convenience of reference, let me just go ahead and write the equation of this just so I can have it to refer to. Is there a function, one of whose level sets is that line? Now, let's write down what we're trying to do. We're trying to figure out, we're looking for some function that when I set it equal to a constant, I want to get an equation that is equivalent to that equation. Now, the temptation is to say, oh, well, the right-hand side is not a constant. I need it to be a constant, and so therefore it's a lost cause. But of course, keep in mind, I don't need them to be typographically identical. I just need them to be equivalent. In other words, identical in meaning. And notice that you could, for example, take this algebra here and rewrite as y minus 2x plus 1 is equal to 0. Now these two equations are equivalent. They say exactly the same thing. Right? And notice that this second one really does fit the desired form. This fits that form. And so, so 0 is the constant, and therefore the function that I'm looking for is y minus 2x plus 1. Or let me rephrase that. An acceptable function. A function, one of whose level sets gives you that equation, is this thing right here, y minus 2x plus 1. And so you'll notice, there we go. Now you might think to yourself, well, hey, what's with the fascination with 0? How come I felt the need to take this constant? That's a perfectly acceptable constant. Why did I feel the need to move that over to the other side of the equation? And no particularly good reason. I didn't have to. A perfectly acceptable answer to this question would have been to leave that there, and then it'd be fine to say, okay, well then we're talking about the level set G inverse of -1 of that function, which is y minus 2x. Totally fine. Right? No issue. Okay. So the answer to the question. Now again, notice when I wrote the answer to the question here, I've written it as a function. By the way, notice there's two input variables here. You can see that right in the formula. This is not a function of x. G, this thing that I said equal to a constant, this is a function of x and y. Which it better be, because level sets always live in the domain. That means that the domain that I'm looking for has to be the xy plane. It's got to be R2. So this is a function, G is a function of two input variables. Okay. All right. Okay. Lastly, is this line an image? Or said differently, sort of grammatically backwards, can I parameterize this line? And of course, this is a chapter 1 problem, parameterizing a line where you have 2 points. Let the difference be the v vector. Pick either one of these points as your x naught vector, and then just write x naught plus tv. That ends up turning into this. Okay, so I think it's interesting to notice that this line, and y'all been doing Algebra 1 for quite a few years at this point, and I hope I expect that you're unintimidated by looking at lines in R2. Right? I don't expect that to be a challenge. But what I hope you will take very seriously and be a little bit afraid of is, are you really thoroughly clear on the proper interpretation and use of the key terms that we're talking about here? Namely, what does it mean to talk about a graph of a function? What does it mean to talk about a level set of a function? What does it mean to parameterize a line? Or what does it mean to look at an image of a function? And note, these three functions that we found are very different. Right? These are three functions that, casually speaking, you might be like, oh yeah, each of these three functions in its own way describes that line. And that's true. But you just can't use these functions interchangeably. Right? If you're using this function here to understand that line, you have to understand that line as being the graph, not level sets. If you understand, we will eventually understand the calculus of graphs and the calculus of level sets. You cannot apply the calculus of graphs to this function in reference to that line. It would make no sense at all. It's absolute meaningless garbage. Right, so it's really important to understand the nature of these connections, the difference between them, and the difference between these corresponding functions. Okay. All right. Next, kind of a similar example, except now it's a plane that passes through three given points. And so, can we find a function whose graph? Can we find a function whose level set? And can we parameterize? And I'm going to let you all work out the details here, but I want to point out these are the answers. It comes from first recognizing that the plane in question has this equation, easy observation, right? These 3 points that we're looking at, not hard to check. X plus Y plus Z is 1. That's the equation of the plane. I want y'all to persuade yourselves that the graph of this F gives you the formally equivalent equation. An appropriate level set of this function gives you the exact same equation. And that the image of this function gives you the exact same plane. Or said differently, all of the points on this image satisfy that equation. Okay, so think it through. By the way, also think to yourself, how would you come up with these? Right? Try to reverse engineer it. How would you have come up with this function here? Think through the process. Again, look, what is the graph construction? How does graph construction work? And think through the process. Okay, skip a bunch of stuff here. These are all good examples. I want you to look at them. Oh, here's the next one I want to do. This is a fun problem. This relates to a homework problem, by the way, which is part of the reason I want to do it. So here's a question. I've got a bicycle, and the wheels have radius 16. I made up. I don't know how realistic that is. And there was a reflector attached to one of the spokes. It's exactly half of the way between the tire, where the rubber meets the road, the tire and the axle. So it's kind of halfway from the center to the circumference. So that reflector, anyone who's been out at night and seen a bicycle going by, kind of nighttime, and there's lights around, the lights hit those reflectors, and you can see the reflectors. Of course, that's the point. But you'll notice that the pattern that reflector makes is kind of like this, right? It's kind of a jumping sort of pattern. How do we describe that algebraically? Is that curve traced out by the reflector? Is that the graph of something? Can I write down, oh yeah, that's the graph of, some function of x? Can I write the equation for that curve? Turns out to be hard to do both of those things. But it turns out to be fairly straightforward to parameterize that curve. So I want to go through the details of that process. Here's our picture. We've got our bicycle tire here. You'll notice that I've got it setting on the x-axis. We're going to view the x-axis as being the road, the concrete. We're going to start with the reflector there. Oh, I should do that in yellow. There's the reflector. And you can use your imagination as this thing starts to roll, as it starts to do that. That reflector is, I don't know, we're going to do something kind of like that, I guess. So how do we parameterize that curve? Okay. Turns out a really great way to break this down is to realize this parametric curve as being a sum of two other parametric curves. And we talked about this in one of the examples last time. Here's the idea. Step one, let's figure out what the axle is doing. There's the axle. There's the path of the axle. Right, if there was a reflector on the axle, well, the axle, as the wheel spins, the axle doesn't really notice the spinning, and so the axle just goes straight line, constant speed. That's pretty easy to parameterize. Okay. All right. So let's do that first. What is the formula that gives position of the axle? I'm going to make a choice here, by the way, that'll seem odd here at the moment, but work with me. My choice is going to be not to use time as my parameter. I'm going to use this angle as my parameter. Note that's the angle between the vertical and the point that was initially in contact with the road. Right? So imagine there's a mark on the tire that at the beginning was right where the rubber met the road, and as the tire rotates, let's look at that mark. Let's look at the angle that makes with the vertical. That angle theta is going to be our parameter. Everybody cool? Everybody on board? Okay. Not hard to persuade yourself that that angle, theta, is the same as that angle. Okay. All right, next observation I want to make. That angle tells me that distance. Right, so how much tire, you look at this this arc of the circle there, that much tire, that's the amount of tire that has been in contact with the road. Right, this is what was initially in contact with the road, and then as the wheels started to spin, then that was in contact, this is the tire that's been in contact with the road. So that's just a matter of angle times radius gives you arc length. Okay. Next observation I want to make, and this is just this is a clever observation that someone made a long time ago. It's very convenient. And that is the amount of tire that has touched road is equal to the amount of road that has touched tire. The amount of road that has touched tire is that distance, aka that distance, namely how far the axle has moved. Right? So it's a clever sort of physical observation. As long as there's no slipping, and this is a rubber road, rubber tire on a dry cement road, so there's no slipping. The amount of rubber that's met road is the same as the amount of road that's met rubber. So we can compute this red distance here as by just taking the angle theta and multiplying by the radius of 16, and that gives us this formula right here. Note the distance traveled, namely the x-coordinate, 16 theta. The y-coordinate, of course, is 16. It's moving in a straight line. The axis is always 16 above the x-axis. The axle is always 16 above the x-axis because the radius is 16. Okay, so we have that. All right, said differently, I now know that vector. And my next question is going to be, let's try to decide, can we figure out that vector? Right, so I found the position vector for the axle. Now I want to find this difference vector between the reflector and the axle. And if I can do that, then we're set, because blue plus purple gives me x. And that'll give me the position vector for x. That'll give me the position of the reflector. That's what I wanted, position as a function of time. Okay, so we already know the blue, so let's get that out of the way. Can we figure out what that vector is? And I'm going to zoom in for focus. Okay, let me do this. Better ink. Oh, come on. Okay, so I want to understand that vector. Now let's think about that vector. I'll remind you that vectors have direction, vectors have magnitude. Vectors do not have locations. Right? So the fact that as the wheel goes along, the fact that this arrow is going to be doing stuff like that, we don't care. Right? The vector, that difference in positions, is I can draw it anywhere I want to. So I find it very convenient, in this situation, to draw a new little axis system over here and just reinterpret that vector over there. And as the wheel turns, then as we drive down the road, this thing is just going to rotate around. This vector here that I've put in standard position, it's just going to rotate around in a circle. Everybody happy with that? It's kind of inconvenient to represent it with an arrow that's constantly doing this. My gosh, that's the difficulty that we're trying to avoid in the first place. It's much easier to just think of it as in standard position, and this distance is not changing. That distance is always 8. And the angle is theta. So that's pretty straightforward. So it ends up being really easy to write down this vector as a function of theta. Now do keep in mind that theta is kind of what you might call upside down, right? The angle's going clockwise around the unit circle instead of counterclockwise, and so that vector is cosine theta. Oh, whoops! I forgot my 8. 8 cosine theta. Negative 8 sine theta. Yeah? Okay. And that's what we have here. So, we figured out where the axle is. The axle is like that. We figured out what to add to the axle's position to get the reflector, namely the difference vector. And so the reflector is just the sum of those two. It's axle plus difference. And that gives me what I'm looking for. Again, what I was looking for is the position of the reflector. And it's that sum. And you can see now why it'd be really hard to interpret. What's the equation for the curve that's parameterized by this? Well, what's the algebraic relationship between these two expressions? Right? It's not clear how we'd go about doing that. That's tough. But the parameterization is easy. Okay, there's several more examples. Oh, I should say, the homework exercise that relates to this bicycle problem is going to start with kind of this, where we are here. And it's just going to ask y'all to do some tweaks of it. So, I've forgotten exactly what the tweaks are. I think in one of them, the bicycle is, instead of going in a straight line on the x-axis, we revisualize the xy plane as being, like a parking lot of slab. Right? And the bicycle is going around in a circle. So, how does that change this? And all you have to do is just note that, well, then this point down here, the point where the rubber meets the road, is going around in a circle. You parameterize the circle. You add that to what this point is doing. Then you have to think about how the axle relates to that point. Then you have to think about how the reflector relates to the axle. Those last two parts are either straightforward or we've already done them. So that kind of thing. So there's going to be twists on this example. Again, several more examples in this section. I think they're all good. They're all twists and variations on things that we talked about last time, things we've talked about today. So I'm going to let y'all read the rest of these and several exercises. Oh, and a heads up. Here's the bicycle example, or the bicycle exercise. Y'all probably noticed on the syllabus that most of the questions in the book are assigned, right? In some sense, when I wrote the book, I only wrote sort of just enough exercises. A lot of textbooks have, 115 exercises per section. I didn't have that kind of time. So they are mostly assigned, but they are not all assigned. That one is not assigned. So pay careful attention on the syllabus. UFRCS 5. Part 4, not assigned. Okay. If you want a challenge problem, feel free to give it a shot. Okay. All right, so moving on to section 2.7, limits and continuity. This is the last section of chapter 2. So we're going to be in chapter 3 starting tomorrow. I told you the summer moves fast. Right? Okay, so limits and continuity. I know y'all have at least some idea of what a limit is. Right, and so there's various different ways that this gets said in a kind of a hand-wavy sort of a sense in single variable calculus classes. And the idea that was told to me one time is, okay, well, a limit means that, if there's some point here where, you look at a graph of a function and there's some point where the function's not defined, then as you get closer and closer and closer and closer and closer to that point where you're trying to approach, and you look at the graph and the curve is getting closer and closer and closer and closer to some little missing, little gap point in there, then that's the limit, right? And the problem with that as a definition is it's got a lot of hand waving in it. And what is the difference between closer and closer and closer? Right? None of this is precise. Right? So it's bad as a definition. Quick historical note. What I'm going to show you as the definition of a limit didn't actually get worked out when calculus was first discovered. So Newton never wrote this down, what I'm about to show you. Newton never really understood this, to be totally honest. Newton kind of did a bunch of hand waving, and he talked about infinitesimals, and we'll just come on, you know what I'm talking about. The lead gets smaller and smaller. This obviously turns into zero, and let's get on with the fact that I've just solved tremendous numbers of engineering problems, right? And the rigor and the formality was pretty much ignored. Didn't get worked out for about 150 years. So anyway, I'm going to show you what they came up with. A nice way to say this is that the function, if you want to say that the limit as x approaches a, the function f is equal to a value L. By the way, this is for a function from R1 to R1. This is single variable calculus. This is what ideally you should have seen in a Calc 1 class, and I know that this usually gets skipped over in a Calc 1 class. But so the idea is that the function f gets arbitrarily close to this value L. Talk about what that means in a second. It gets arbitrarily close to the value L when x gets sufficiently close to the value A. Okay, and it turns out there's a great phrasing. Arbitrarily close. What do we mean? What does it mean, arbitrarily close? Arbitrarily close means no matter how close you want the function to get to L, we can make sure that it's that close to L. Arbitrarily, I mean, as close as you want it to be. So, we're going to indicate how close f is to L. Here, I better go into pen mode. We're going to indicate how close f is to L by looking at that distance and requiring that distance be less than, whatever our amount is here, whatever that radius, I've got it drawn over here, whatever that radius is, call it epsilon. So arbitrarily close could be phrased as no matter how small epsilon gets, then under some circumstances I need to ensure that this distance is less than that threshold or that requirement. Or said differently, I need for that distance to be smaller than this radius, you might call it. Or said differently, I need the absolute value of f of x minus L to be less than epsilon. Okay, so going back to the definition, arbitrarily close, we're going to represent as, hey, no matter how close, no matter how small epsilon is, no matter how close you need to get to L, there's something that we can do, we'll talk about that in a moment, to ensure that f is indeed that close to L. The distance from f to L is, as required, less than that tolerance, epsilon. Okay, so that's what we mean by arbitrarily close. Okay, so we need to be able to assert that the function gets arbitrarily close to L. When x gets sufficiently close to A, now what do we mean by x gets sufficiently close? That means I need to be, with my green goal in mind, of making f as required, arbitrarily close to L. I'm going to do so by requiring that x be close to A, and I get to pick how close I need x to be to A. There needs to be some notion of sufficiently close to A that gives me the arbitrarily close that I need. So here it is. How do we describe how close x is to A? Well, same kind of picture, really. I need to ensure that x is as close to A as, no more than a certain distance away from A. And I'm going to characterize that by this distance being less than my tolerance. I'm going to call that tolerance delta. And I'm going to write that algebraically as I need the absolute value of x minus A, that means the distance, to be less than delta. So, in my goal to make f arbitrarily close to L, I simply need to know that there is some sufficiently small delta that makes x what I'm going to call sufficiently close to A. And what I mean by sufficiently close is that this requirement of how close x is to A has to be sufficient to give me what I'm interested in. I need to get, as desired, f, as close as is required, arbitrarily close to L. Okay, so let's read through the whole thing then, all together. I don't mean all of us together. I mean all together in the sense of I read the whole thing all at once. For every epsilon greater than 0, keep in mind epsilon represents a tolerance, a distance. Wouldn't make any sense for epsilon to be negative or 0. That doesn't make any sense at all. For every reasonable choice of epsilon representing how close I might need f to get to L, whatever that epsilon is, I need for there to be some value delta representing, again, a distance, a tolerance. Again, it doesn't make sense for that to be anything but positive. No matter how arbitrarily small epsilon is, I need for there to be some sufficiently small delta so that that delta, as a requirement on x, in other words, insisting that x be that close to A, I need for that to give me, to ensure that f of x minus L is less than epsilon. Namely, that f is, as desired, as arbitrarily close as was required to L. So that's the definition. It works really well. Primarily, really good thing about this definition is it doesn't involve any hand waving. It does not involve any vague references to closer and closer. Right? These are all very precise mathematical symbols. There's no question about what these mean. Right? Also, this definition does not make any sketchy references to stuff like infinitesimals. What's that? What's an infinitesimal? Some of y'all may have heard of infinitesimals. Some of your calculus classes in high school may have even made reference to infinitesimals. People talk about dy over dx as being a ratio of infinitesimals. Depending on your perspective when this was explained to you, you might have just swallowed that. It turns out it doesn't make any sense at all. Infinitesimal number. A number that's infinitely small? What is that? Right? It doesn't really make any sense. There are no real numbers that are infinitesimals. So it's if you define limits in terms of infinitesimals and this assertion that there exists a notion of infinitely small, it's not at all clear what you're talking about, and it basically doesn't make any sense. Okay, so this bypasses all of the meaningless nonsense that very often is tossed around in high school classes. Okay, all right. One other little thing. Why do we put this in here? Why do we put that x minus a greater than 0? Let's think through what the consequence of that greater than 0 is. The consequence is that, keep in mind, I need for these values of x to always satisfy this condition. Any x satisfying this has to satisfy that. Without the greater than 0, I would need all of the values of x in the interval. I need all those values of x to satisfy this requirement. But by saying x minus a greater than 0, that means I'm only responsible for values of x. Here, let me zoom in so I can draw focus better. I'm not responsible for all of these values of x. I'm only responsible for the ones where the distance to A is not 0. So I'm not responsible for A itself. Right? I don't need for f of a to be arbitrarily close to L. I just need f of these nearby values of x, not a itself, just the nearby values of x. I need those values of the function to, do what they're supposed to do. I don't need f of a to do what it's supposed to do. Now, why is that an appropriate choice here? Well, let me just remind you, large part of the reason why we need to talk about limits is that the value of the function may not be defined at the point. The whole reason you're interested in limits in the first place, I'll say usually, is that the function's not defined at a in the first place. Right? So having a definition of limit that requires for the function to be defined at a and for that value f of a to do certain things would defeat most of the purpose of having limits in the first place. Okay. All right. So you're not responsible for the function being defined at the point in question, and you're certainly not responsible for any conditions to be satisfied there. Okay. All right, so that's all Calc 1, and now I'm going to talk about the multivariable version of that. First thing I'm going to do is I'm going to redraw this picture. Let me notice what's happened on this picture. As drawn, notice on the x-axis, there's the value a that we're approaching. There are references to this value x that is approaching a, right? And we have this value delta that represents, the notion of sufficiently close. So this number represents our sort of a radius around a. Okay. Notice as well on the y-axis, there's L, the limit that we're trying to define. There's the value of the function, f of x, right? And there's this value epsilon giving us again our radius. Okay. All this stuff in here is just a visual aid to help us sort of see, get geometric satisfaction of what it means to require that these values of x give rise to f of x's that do a certain thing over here. I don't really need to have drawn this. I drew this in the graph context because it'd be familiar, gives you some sort of geometric satisfaction, right? It's not really necessary to draw that picture in writing down this definition. So I'm going to redraw the picture in a different way I'm going to draw the x-axis, I'm going to draw the y-axis, I'm going to draw all the players on those two axes, and that's it. There's the x-axis and all the players on the x-axis. Here's the y-axis and all the players on the y-axis. And now let's just think of the function. Forget graphs. Again, graphs are very limiting, very confining dimensionally. It's a big problem. Graphs are really inconvenient when you're talking about multivariable functions. Here, I'm just drawing the domain over here, target over here, and I require that no matter how small this interval is, there must be some sufficiently small interval over here such that all of these values of x, not a of course, all these values of x give rise to f of x that do what they're supposed to do. Everything you really need to see is there. Okay, now why do I do this? Well, because in trying to generalize this definition to a multivariable function, three-dimensional graphs are really hard to draw, they're really hard to work with, they're really hard to make sense out of, and it's just not a convenient way to do business. So here, though, I can redraw the picture. I can make a multivariable version of this picture pretty easily. Here, I'm representing a function f from R2 to R1. I could reasonably ask, as this point is no longer a number, this point x approaches this point, no longer a number. Factor, you might say. This point A, what does it mean, as x approaches A, what does it mean for f of x to approach L? What does it mean for this L to be the limit of this function? Well, same deal. Arbitrarily close interval, epsilon radius. notion of sufficiently close. Namely, I need for that vector x minus a to be shorter than that tolerance. Or said differently, I need for this point x to be within not an interval centered at A, but within a disk. Let's say a disk centered at A. So it's just it's a sort of a two-dimensional version of the definition that we have above. The way you write it down on the page, practically identical. This idea of sufficiently close, distance from L characterized by a maximum allowable radius epsilon, just like in the single variable definition. Oh, why did I erase that? And this idea here that x is inside of this disk, I just need the magnitude of the x minus a vector to be less than delta, and there's that. There needs to be some delta such that x is within that ball, that disk, or said differently, the magnitude of the x minus a vector needs to be less than delta. So note the familiarity of what what this definition ends up looking like. It cosmetically looks exactly the same. The only difference is that instead of this being an absolute value, now it's a magnitude of a vector, magnitude of a difference vector, instead of absolute value of a difference of scalars. So very, very similar definition, very, very similar motivation, and it's similarly practical. Okay. All right. Now, in practice, how do we compute limits? Do we actually, day in and day out, fiddle with epsilons and deltas? And thankfully, no. That said, there are some exercises that are going to ask you to not exactly use the entire definition here, but I'm going to ask you to play certain games like, certain question, we've got some function, we're approaching some value, the limit is alleged to be a certain candidate value, L. For a given epsilon, how small does delta need to be for this to work? Right? You just have to think through, for smaller values, as delta gets smaller and smaller, when does this condition actually get satisfied? And just, draw the picture, think it through. And there'll be some multivariable versions of those same things. Okay, now in practice though, day in and day out, we don't use epsilons and deltas very often. There are different methods for computing multivariable limits. There's, I guess, sort of three methods that I'm going to talk about here. The first one is very convenient when it applies. It only applies sometimes. Don't inadvertently over-apply this idea because it doesn't work, except in the very special circumstances, and that is if you're looking at a multivariable limit and if you are approaching the origin. It turns out that if you think about it, approaching the origin is the same as saying your polar coordinate r is approaching 0. Just draw the pictures. Right? Whoops, wrong color. Saying that x comma y is approaching the origin, that's equivalent to saying that this distance r is approaching 0. I mean, if r is approaching 0, that point has nowhere to go but the origin. And furthermore, if the point is approaching the origin, that r is going to have to approach 0. They're simultaneous ideas. And the beautiful thing about this observation is that while this is a multivariable limit, and multivariable limits are a brand new idea that we're just seeing here today for the first time, we don't really have methods, and I don't know what we do with this, right? This, instead, that's a single variable limit. So it effectively, this observation about polar coordinates turns a Math 212 problem into a Math 111L problem. It's a single variable. Okay. Yeah.
Can you do this in 3 dimensions?
Yeah, there's a 3-dimensional version, where you have spherical coordinates and where it's rho. Yep, totally. Now, observation. This only works if you're approaching the origin. Right? It's got to be the origin, non-negotiably. Right? Because that's the only point that, as you approach, as R approaches a certain value, that insists, that forces the point itself to approach a single point. Right? It doesn't work for other values of R. So only if R is approaching 0, only if the point is approaching the origin. Anything else doesn't work. So let me show you an example of how handy this can be. Let's think about that multivariable limit. It's a multivariable limit I don't have methods for particularly, so what do? And step 1, let's just convert into polar coordinates. By the way, note my denominator, x squared plus y squared, that's r squared. Right, my numerator, x cubed y squared, let's memorize that for a second, x cubed y squared. And all I have done here is plug that in. Here is x cubed y squared. The denominator, same deal, x squared plus y squared. Well, we've already observed that that's r squared, and you can multiply out the trig if you'd like, but you can see that this is going to turn into r squared. Right? We have a grand total of 5 factors of r up there, canceling the 2 factors of r in the denominator, thus leaving a leftover of r cubed. And then don't forget the cosine cubed sine squared. Right, so grand total then, this multivariable limit simplifies into this single variable limit. Now, question, quite awkward question. What do you do with the thetas? And the answer is we don't have any control over the thetas. I know that as you approach the origin, here's the origin, as you approach the origin, r is clearly approaching 0. But theta, I don't know. Theta could be, I could be approaching along this curve here, in which theta is, that value. Or I could be approaching along this curve, in which case theta is a different value. Or much worse, I could be approaching the origin along a spiral, in which case theta is not even constant. Theta is varying. Theta is approaching infinity, or, oh my gosh, I have no idea or control over what theta is doing. So there's a temptation to look at this and say, well, I don't even know. I'm looking at an expression here, and I don't even know what some of the variables are doing. How can I possibly make any sense out of this expression? And the way we work with this, as it turns out, and again, fingers crossed, this only works if it works, right? So everything's got to line up. First, notice that this is a product. Recall from single variable calculus that the limit of a product is the product of the individual limits if those individual limits both exist. Okay. Well, that's not actually going to help us because I don't know what the limit of the blue thing is, right? So that doesn't help. We don't know what theta is doing. I certainly don't know what the limit of this expression is. But I do know what the green limit is doing. Right? The limit as r approaches 0 of r cubed, 0. So what I have here is I have something that is approaching 0 being multiplied by something else. Now, you might recall L'Hopital's rule, indeterminate forms, and hey, just because part of it is approaching 0, well, the other part might be approaching infinity, and we could have an indeterminate form. There could be something weird here, right? But that's not happening here. What I can say about this blue expression is, as much as I have no idea what theta is doing, I have no earthly clue what theta is doing, I do know for sure that cosine is always between -1 and 1. Sine is always between -1 and 1. Therefore, this product is always between -1 and 1. So I have something approaching 0 times something that's bounded. And that limit's going to be 0. That make sense? Sandwich theorem. Sometimes it's called in single variable calculus class. Okay. All right. So So we get 0 in this case. All right, now here's what could go wrong. Your original limit might not be approaching the origin. Game over. You can't apply polar coordinates. This denominator might not have worked out so simply. I mean, wasn't that convenient? We got rid of this ugly denominator by just, hey, the sine squared plus cosine squared is 1, and the r squared is canceled, and there's no denominator left. That might not work out in another example. In which case, again, you're out of luck, probably. I mean, take a look at the peculiars of the situation, but it might not work out. And then lastly, the thing that is approaching 0, the rest of it might not be bounded. Right? If this was cosine theta divided by sine theta, that's not bounded. Argument fails. Right? Be careful with that. So it's only if the expression is bounded that you can apply this argument. So this argument's a great argument. It works surprisingly often, but it is not. It doesn't work really all that often in some sense. Okay. All right. Let me show you an alternative point of view to take on limits. Correction. Let me show you a tempting point of view on limits, and that is. Forget about this whole epsilon and delta stuff. Wouldn't it be convenient to let's just parameterize this point? Whoops, wrong color, or wrong pen. Let's just parameterize that point x approaching a by let's just write x. X is a plus tu. Let's let u be a unit vector pointing in some direction. Tu then is this difference vector, and as t approaches 0, if t approaches 0, then x approaches a. Right? Why can't we just do this? Why can't we just say, look, let's just write it down, x, wherever it is, let's write it as a plus tu, let's let t approach 0. Why can't I just look at that limit? Well, the answer is, I need to consider all different directions from which I might approach. Right? Okay, so let's modify our attempted rewrite of the definition of a limit. Let's say, no matter which direction you're approaching from, what if, in other words, for every unit vector, if it were true that for every unit vector, approach, by a plus tu, let t approach 0, that's simultaneously considering all possible directions from which you might be approaching a. All possible directions. Shouldn't that be equivalent to the definition of a limit? So here's our candidate. No matter what direction you're approaching from, every possible unit vector. Here's x approaching a by t approaching 0. And let's suppose that no matter how I do it, suppose I always get the same value, no matter which direction you approach from, every possible straight line direction, you always get the same value, L. Shouldn't that mean that the limit is L? It's extremely tempting. Lots of students leave a multivariable calculus class thinking that this is what a multivariable limit is. And very importantly, this is not right. Very importantly, this is wrong. Of course, I gave away the game there. I should have done a page break in the book there so I could, keep the surprise. So this does not work. It's just not equivalent. And I'm going to show you an example of what goes wrong. Here's the function I want to consider. Given a point x, I'm going to define this function called the theta function. Oh, come on. I'm trying to draw a straight line. Good enough. Theta of x to be that angle. All right, and very importantly now, let's see, where did I write this? Here we go. So on the x-axis itself, I'm going to define theta to equal to 2 pi, not 0. It's a minor little tweak, right? Very often we would choose theta to equal to 0 on the x-axis. Let's not. Let's choose to define this function, the theta function, to be 2 pi on the origin end. The nice thing about this now is that this theta function I've got defined is never 0. Right? The theta function over here, theta is small. Over here, theta is a little bigger, 2 pi. And then if you move ever so slightly back into the first quadrant again, it skips right over 0 and just goes into small numbers. Okay, so that's my choice for this this function theta. Now I'm going to define a function f by this formula there. This is defined everywhere in R2 except for the origin. Very simple formula. It's just the magnitude of x divided by the angle, this theta function of x. Right? And I want to entertain what this function is doing as you approach the origin. And we're going to start off taking our candidate. We're kind of intrigued by the idea of understanding limits, in straight line approaches. A plus tu, and we're going to let t approach 0, and so we're sort of approaching the origin along straight lines. What do you get for this function along straight lines? And the answer is you always get 0. Every straight line path, you always get 0. And no surprise. Let's just think it through. Suppose from this point you approach the origin along this straight line. Along this straight line, theta is not changing. Everywhere on this, as you approach the origin on this straight line, that's not changing. That means this denominator is not changing. It's constant. And as you approach the origin, magnitude of x clearly approaches 0, and so you get 0. So along every straight line path, even if you approach along the x-axis, theta is 2 pi, constant. You still get 0. Every straight line path, you always get 0. It'd be pretty tempting to say that the limit of this function is 0. And that would be a really, really catastrophic thing to settle on. Let me show you why that would be a problem. I'm going to choose a different path to approach along. I'm going to approach instead along a spiral. This is the spiral defined by r equals theta. Now let's just, think through, do a polar plot. What happens if r is equal to theta? Well, for small values of theta, you get small values of r, and so you're really close. As theta increases, you get increasingly far away from the origin, and that just has you kind of spiral out. Right? So let's approach the origin along that path. R is equal to theta. And keep in mind that what that means, wherever I might happen to be, let's say here, at that point, if r is equal to theta, well, that being r, if that's equal to theta, then notice what you get is theta divided by theta, which is 1. That's the really, really creepy, downright creepy, weird thing that happens. Every straight line direction that you approach along, this function's approaching 0. No exception to every straight line path. All 0. Every direction, no matter which way you go. But if you bend it in along this curved path, you get 1, which is very much not 0. Right? And that is highly inconsistent with the idea that the limit of this function should be 0. How could the limit be 0 if from one along some path you're getting not 0? It doesn't make any sense. Right? Think back to single variable calculus. If the left hand limit and the right hand limit give you different values, the limit doesn't exist. That's not a thing. All right. Okay, so moral of the story, it is very hard to understand multivariable limits from the point of view of single variable limits. Multivariable limits are intrinsically more complicated. They're more difficult, and it's very dangerous to try to understand multivariable limits from the point of view of single variable limits. Certainly, at least along straight line paths. Now, that being said, there is a way to fix this. The way to fix that is instead of considering just straight line paths, if you consider all possible paths, and let me draw a picture just to emphasize. If, as you approach A, there's your A, if along all the straight lines, all the spirals, all the knuckleballs, all the, let's see here, spirals going the other way, indecisive knuckleballs, every possible weirdo path that you could possibly consider. If along literally all paths, I don't know how to enumerate that. How do you enumerate all paths? If you think about it. I mean, I just made up some random weird stuff, but that's just a short list of random weird curves. Bet you I cannot come up with a list of all random weird curves. I'll bet you no matter what list of random weird curves I came up with, you could come up with a different weird curve that I didn't think of. Right? So it's hard to figure how you would accomplish this task, but if it turns out it's true that if along every continuous path, if the limit along that individual path is always equal to the same value L, then yeah, it turns out that that is sufficient and the limit actually is equal to L. So this is a satisfactory reinterpretation of the definition of a limit. Now, useless, you might say, because I can't consider all possible paths, but we can turn this theorem around backwards. If, as this says, multivariable limit exists implies that I will always get the same answer no matter which two paths I pick. Well, that means that if I were to approach along two different paths and if I were to get different answers, this couldn't possibly be true. Therefore, the limit could not possibly exist. Right, so what we have here is, turning it around backwards, tools for identifying when a limit fails to exist. And here's two of them. I'll talk about the second one first. If there exist two paths that approach A, and if the limit along the one path is not equal to the limit along the other path, then the limit does not exist. Don't try to compute it because it doesn't exist. Okay, we'll talk about how to actually put this into action, and we're going to literally start taking paths. We're going to start generating paths and plugging them in and computing individual limits like this. And with our fingers crossed, hoping that as I compute individual limits, just hoping that maybe I'll get two different answers that are different from each other. At which point I say, oh, they're different, two different paths, different limits, limit can't exist, I'm done. End of story. Along similar lines, if there is any single path along which the limit, even along that one path, does not exist. Same conclusion, the multivariable limit does not exist. Okay, let's see some examples. Here's multivariable limit. I'm going to start thinking about different paths. Interest of time. So I started off here by parameterizing just along the y-axis. I'm going to let you all read that part. I'm going to skip to where I do something more substantial down here. I'm going to approach along this straight line y equals mx. You can persuade yourself that if you're approaching along this line y equals mx, that here is a parameterization of that path. Now there's that parameterization concept we talked about, right? So parameterizing curves is going to be important in understanding multivariable limits. This is the graph parameterization of the function whose graph we're looking at here. So if you want to approach along a line y equals mx, Here's the parameterization. Now, what do we do with the parameterization? Well, I'm going to plug that parameterization. Whoops. I'm going to plug that parameterization into the function. Keep in mind what a parameterization is. A parameterization is telling you that that is your x. This is your y, and so the x and the y, I mean, that's what a parameterization is x and y as functions of t. Take the x and the y in the parameterization, plug them right on in to the limit you're trying to compute, see what you get. And in this case, notice what happens. Plugging in the parameterization, we get this multivariable limit. The t's cancel. We have the limit of a constant. That gives us a constant. M over 1 plus n squared. Okay, now let's interpret what just happened here. I just computed the limit along a particular path, y equals mx. Actually, I just computed the limit along a bunch of different paths because I never said what m was. Right? So if m was 1, then the limit along that path is 1/2. Right? If m is 5, then the limit along that straight line, it's a different straight line, m equals 5, I get 5 over 26. If m is 10, then you get, any different value of m, you get a value of this limit. And very importantly, note that these are different, right? Depending on m, this expression takes different values. So along different straight lines, we're getting different answers. This limit does not exist. The multivariable limit does not exist. Everybody on board? All right, several more examples here. Now do be careful. Let's go through this example here. Looking at that multivariable limit. By the way, you might look at this multivariable limit thing. Hey, we're approaching the origin. Hey, let's use that polar coordinates thing. I love that. The polar coordinates thing was really nice, right? It's going to crash and burn badly here. Yeah.
That's the zero vector.
Yeah. It's the zero. So it's 0, 0.
Right.
Yes, the origin. However you want to say it. Yeah, totally. Yeah, now this is going to crash and burn badly because of that exponent. There's a 7th power there. So this is not x squared plus y squared. It just, and if we plug in the polar coordinates, it just doesn't simplify at all, and it's not. You can't go anywhere with it in polar coordinates. And you can in this previous example. The polar coordinates would give you. It would give you a different expression that you could argue along straight lines that would give you different answers. You get the same conclusion, but algebraically it'd be a little bit different. But you could totally do it. Yeah. It wouldn't really serve much of a purpose because you'd still have to make this argument along different lines. Yeah. Okay. So let's look at this one. So we're going to start doing straight line parameterizations. Same straight lines, y equals mx. Same parameterization, graph parameterization, x is t, y is mt. That does all the straight lines, right, approaching the origin. Plug it in, you get this expression. Well, you get this expression, which is equal to that, after you cancel some common factors of t. And you got to think about this now. What happens? What is this limit as t approaches 0 of this expression here? The limit of a fraction. Remember that the limit of a fraction is the fraction of the individual limits if those two limits exist and if the limit of the denominator is not 0. And that's the case here, right? The numerator is approaching 0. The denominator is not approaching 0. The denominator is approaching m squared. So this limit is 0 over m squared, which is 0. Okay. By the way, I urge y'all to all make sure that you're really good with single variable limits. Again, Calc 1 is in the prerequisite trail of this course. And so I assume that you're really good with single variable limits. Make sure you understand the difference between an indeterminate form and just a fraction. Right? They're not the same thing. You can only apply L'Hopital's rule or indeterminate form methods if, in fact, it's an indeterminate form. right? So make sure you're really good about those differences and thus that you can compute single variable limits appropriately. Okay, now what's happened here? I've looked along all the straight line paths. Along all those straight line paths, I always get the same answer. Every single direction that I approach from, I always get 0. Resist the urge to declare the answer to this question to be 0. Right? Because we already saw an example where, just because along the straight line paths you get one answer, that it doesn't mean that there might not be some spiral or knuckleball or some other wacky curve along which you get something different than 0. So anyway, this is a disappointment. We were hoping to get different answers for different m's. Tragically, we got the same thing. It works too well in some sense, and we have no conclusion. Okay, next idea. Let's approach along a curve. Let's approach along this parabola. Graph parameterization. Make sure you can do that, right? Make sure you're comfortable with how to get a parameterization from an equation. Okay. Use the graph parameterization if you can. Plugging that parameterization in to the function. Compute. And you get 0 again. Now, we got 0 previously. We got 0, all straight lines give you 0. Now we look along a parabolic curve. We got 0 again. No contradiction, no conclusion. I have not yet checked all possible paths, so I can't just say, oh, come on. I'll keep getting the same answer here. What are we doing? Right? Doesn't it really look like the answer ought to be 0 here? The argument simply doesn't hold water. And then look what happens when we try along cubics. There's a cubic. That's how you parameterize the cubic. Plug that into the function. You get 1, not 0. And so the game is over at this point. We had a bunch of zeros. It was looking like they were all going to be equal. It was looking like it was going to be, that the limit was going to be 0. And then we found a path along which we get a different answer. Game over. They lose. The limit does not exist because these two values are different. Depends on how much time you have. Let me emphasize one thing. This is a fair class. I will never ask you a question to which I have not given you methods that will allow you to determine an answer. Right? I'm not a monster. Right? And I'll note that there are plenty of functions out there where the methods that I'm going to show you, nothing would work. I will not put one of those on the exam. Right? So this is just something that works in some cases. Right? In some cases, this trying different paths thing will give you a contradiction, and you'll be able to conclude that, the limit doesn't exist. In some cases, you'll keep getting the same answer. Every time you're like, oh my God, how far do I go with this? And then you might think, did I try the polar thing? Hey, maybe the polar thing might work. There's another method I'm going to show you on tomorrow, right? You just got to keep trying different things until something works. I promise that something will always work in this course. And I realize I'm out of time now, so I'm sorry I had to go a little bit over. Okay, see y'all later.